Imagine a multi-million-dollar robotic arm, right?
Yeah.
Like, it is perfectly calculating the microphysics of gripping a ceramic mug.
Right, tracking every single millimeter of its own movement.
Exactly.
Yeah.
It adjusts its servos with, flawless precision, and then it just aggressively smashes that mug directly into the countertop because, well, it completely forgot it was trying to pour coffee.
Yeah, which is the classic problem. You have perfect physics, but absolutely zero common sense.
Right. And when you're building systems to predict the physical world, you constantly run into this fundamental tension. You're trapped between optimizing for local precision, knowing exactly where your end effector is right now, and global semantics, which is actually knowing the ultimate goal of the trajectory.
And that tension, I mean, that is the defining bottleneck in predictive modeling right now. It's the classic local versus global optimization problem. You build a model that meticulously tracks high-frequency changes in continuous space, and, well, it becomes totally blind to the long horizon intent. But the moment you try to feed it that global context, it usually just loses its grip on the physical precision and starts hallucinating.
So today, since you listening likely spend your time wrestling with these exact architectural trade-offs in machine learning and data science, we're skipping the introductory concepts. We are jumping right into a deep dive on a highly technical solution to this exact local global problem.
Yeah, it's presented in a paper titled ThinkJEPA, Empowering Latent World Models with Large Vision Language Reasoning Model.
Right, which is a massive collaborative architecture from researchers across Northeastern, UCSD, UMD, UT Austin, and UW. And their specific target here is the vulnerability of latent world models, particularly the VJEPA-2 architectures.
Yeah, so to really appreciate the solution here, we have to look at how a model like VJEPA actually operates, because they are brilliant at predicting high-level structures and fine-grained dynamics from video observations.
And they do it entirely in representation space.
Yeah.
Yes, exactly, which saves the massive computational overhead of decoding back to pixels. But, their fatal flaw is the severely limited temporal perspective. They rely on densely sampled, very short observation windows,
which mathematically biases the predictors toward local low-level extrapolation. I mean, if you only give the model a fraction of a second of dense frames, it can map the trajectory of a moving hand flawlessly for the next few milliseconds.
right?
But it cannot tell you if that hand is reaching for a cup, pushing a block, or like waving away a fly. The long horizon semantics simply do not exist in that tiny perception window.
Right, and the mission of the ThinkJEPA architecture is to solve that exact temporal blindness. The authors developed a method to bridge those dense predictive architectures with the open vocabulary, long horizon semantic reasoning of large vision language models.
The VLMs.
Yeah, the VLMs. And the crucial engineering feat here is that they achieve this fusion without falling into the very common trap of trying to use the VLM as the actual trajectory predictor.
Which is usually the first instinct, right? I mean, since you and your teams have access to massive, highly capable VLMs like Qwen3VL, the immediate engineering thought is, well, just feed the video into the VLM and prompt it to predict the future physical states.
Yeah, you think, we have the compute, why even bother maintaining the GPE backbone?
Exactly. So why doesn't that work?
Well, that approach completely breaks down when you look at the underlying math. And the authors deconstruct this standalone failure beautifully. The first structural wall you hit is compute-driven sparsity.
Yeah.
Video VLMs operate under the constraints of quadratic attention costs. So as the sequence length grows, the memory and compute requirements grow quadratically.
Right, the memory blow up.
Exactly. You simply cannot feed a high FPS, densely sampled video over a long horizon into a VLM without immediately bottlenecking your GPU memory.
So to avoid an out-of-memory error, you're forced to sparsely and uniformly sample the frames. You might take, 1 frame every second instead of 30 frames a second.
Right.
But when you do that, you mathematically destroy the high-frequency temporal data you need to model physical reality. Like, you completely miss the exact frame where a finger makes contact with an object or where a trajectory subtly shifts due to friction.
Yeah, that's the compute limitation.
Yeah.
But even if we assume, you had infinite compute and could feed dense video into a VLM, you hit the second, more fundamental issue.
Which is?
The language output bottleneck. Just look at the architecture of any modern VLM. The deepest transformer layers are entirely optimized to compress fine-grained, continuous visual and interaction states into discrete, text-oriented representations.
Ah, right. The loss function pushes the entire network toward language generation.
Exactly. Which means the output is perfectly coherent in text, but structurally useless in continuous metric space. I mean, it knows the discrete word grasping, and it can describe a grasp flawlessly.
But grasping in text covers like 10,000 different continuous micro-adjustments in physical coordinate geometry.
Precisely. The VLM compresses all that metric nuance into a single semantic token. And furthermore, trying to fix that language bottleneck by taking a massive foundation VLM and fine-tuning it heavily on a specific, dense action dataset, well, that leads to a third problem, which is catastrophic forgetting.
Oh, of course.
The moment you force the network to prioritize metric space physical prediction, you overwrite the generalized world knowledge and semantic reasoning that made the VLM useful to begin with.
So that clarifies the baseline failure modes perfectly. It's like using a VJPA model on its own is like driving a car while staring strictly at the pavement 3 feet in front of your tires.
Right.
You will dodge every immediate pothole with incredible precision, but you will completely miss your highway exit, because you have literally zero global awareness.
Yeah, that's a great way to put it.
And conversely, relying on a VLM to predict physical trajectories is like navigating strictly by staring at a zoomed-out GPS map. You know exactly where your ultimate destination is, but you are going to crash your car immediately because you aren't looking at the actual physics of the road.
That analogy maps directly to the paper's core synthesis. VLMs must be utilized strictly as semantic guidance providers. They give you the GPS route, but the dense trajectory prediction, the actual steering of the car that has to remain within the specialized latent world model.
Which introduces a massive architectural headache, right?
Oh, absolutely.
Because if we acknowledge we have to keep the VLM out of the direct prediction loop, how do we actually fuse these completely distinct temporal scales? You have a dense, high-frequency stream of data and a sparse, low-frequency stream of semantic concepts. How do you merge them without creating a computational bottleneck or, blurring the signals together?
So the authors solve this through a two-branch architecture that they call the dual-temporal perception field.
Okay.
The first branch is the dense JEPA pathway. This utilizes a VJEPA-L backbone operating with a highly dense 1024-dimensional latent space. This pathway processes a densely sampled, very short observation window.
Because it needs the microphysics.
Exactly. Because it has access to every consecutive frame in that tight window, it extracts spatial patch tokens that perfectly preserve the high-frequency physical interaction cues.
Okay, so that is the local physics engine. Then the second branch handles the global context.
Right. The second branch is the VLM thinker pathway. It takes a uniformly sampled clip over a much larger temporal stride, giving it a broad, sparse view of the action over time.
Got it.
It feeds this long horizon view into Qwen3VL, which acts purely to capture the entity relationships, the overarching context, and the ultimate semantic goal of the sequence.
Okay, so the theoretical separation of duties makes total sense, but injecting global context is notoriously tricky. If the VLM branch operates on a sparse, low FPS signal, its outputs are inherently broad and generalized.
Very broad, yeah.
So if you just dump those core semantic outputs into the highly sensitive, high-frequency dynamic tokens inside the JEPA-predictor, don't you risk washing out the local precision? Like it feels like overlaying a blurry, low-resolution map on top of a high-definition photograph. You risk destroying the precise physical awareness the JEPA model just worked so hard to extract.
Yeah, and that is the exact vulnerability that ruins most hybrid models. Navigating it requires a highly specific extraction and injection strategy. The authors don't just dump the final output of the VLM into the GP model.
Right.
They designed a hierarchical pyramid representation extraction module. And the first critical rule of this module is that you never pull your semantic features solely from the final layer of the VLM.
Oh, because of the language bottleneck we discussed earlier.
Exactly. By the time the forward pass reaches that final layer, the continuous spatial data has been heavily quantized into a discrete language concept. The visual reasoning cues are already lost to the text of tokenization.
Right. The nuance is gone.
Right.
So what do they do instead?
Instead of relying on the final layer, the architecture extracts intermediate hidden states across the entire depth of the network. They specifically pull from layers 0, 4, 8, 12, 16, 20, 24, and 27.
Wow, so skipping through the whole network.
Yeah. And on top of that, they capture the visual tokens straight from the vision transformer tokenizer before the language model even begins processing them.
Pulling from specific layers like that feels very intentional. It operates a lot like gathering intelligence from different levels of a corporate hierarchy.
Yeah, that's a good way to think about it.
Like you pull from the VT tokenizer and the early layers, the frontline workers, to get the raw visual materials and low-level shapes. You pull from the middle layers, middle management, to understand the spatial relationships and object tracking. And you pull from the deepest layers, the executives, to get the high-level semantic goal. You capture the entire progressive reasoning trace of the VLM without committing to the final quantized text output.
Yeah, that multi-depth pyramid approach ensures you have a rich hierarchical semantic guidance vector. But, that brings us to the second half of your earlier challenge, which is the injection phase.
Right.
The VGPay-predictor block operates at an internal dimension of 384. So how do you mathematically fuse this massive, multi-layered hierarchical representation from a VLM into a 384-dimensional latent dynamics predictor without disrupting the delicate sequence modeling?
Well, I feel like a lot of engineers listening would instinctively reach for a cross-attention mechanism here, since that is the default way to fuse modalities in modern transformers. You just let the GP tokens attend to the VLM tokens.
Right, and the authors actually ran extensive ablations on that exact assumption, testing both cross-attention and adaptive layer normalization, or ADLN. But they ultimately chose a technique called feature-wise linear modulation, or film.
Okay, Phil.
Yeah. And understanding why Film 8 cross-attention is crucial to understanding how latent world models actually simulate physics.
Let's dig into that mechanical difference then, because choosing film over cross-attention goes against a lot of current conventional wisdom in multimodal architecture.
It really does. It all comes down to how cross-attention alters token interaction. Cross-attention routes information based on semantic relevance, right?
Right.
So if you use it to inject the VLM data, it allows a patch token at time step 1 to heavily attend to a semantically similar patch token at time step 10, while potentially completely ignoring time step 2.
Oh, I see where this is going.
Yeah. A JEPA model's entire ability to predict physical reality relies on the strict, unyielding spatiotemporal positioning of those tokens. It learns physics by tracking how a specific patch changes sequentially from frame to frame. So if cross-attention scrambles that rigid spatial grid to prioritize semantic relevance, well, the physics engine essentially breaks.
So cross-attention fundamentally alters the sequence order, whereas film preserves it.
Exactly. With film, the semantic guidance features from the VLM pyramid are mapped to per-layer modulation parameters, specifically a scaling vector and a shifting vector. So as the dense tokens pass through the VJPay predictor blocks, the film layer simply performs an affine transformation on the predictor's inputs.
So it literally scales and shifts the latent features channel by channel based on the VLM semantic guidance. It modulates the intensity of certain features, like amplifying the channels relevant to grasping and suppressing irrelevant noise without ever rearranging the spatial temporal structure of the tokens.
Precisely. And empirically, the ablation studies prove this. Film achieved the lowest feature distance between the predicted latents and the ground truth latents. It modulates the physics without scrambling the geometry.
That theoretical elegance of using film to preserve the spatial grid is compelling. But, latent space is notoriously fragile. If you inject semantic data this way, we need to know if it actually survives in downstream tasks or if it just looks theoretically sound during training.
Right, does it actually work?
Yeah, how does this architecture actually perform on complex metric space forecasting benchmarks?
Well, to prove the architecture, they evaluated ThinkJEPA heavily on EgoDex and EgoXO4D. And for context, EgoDex is a massive, highly complex benchmark focused on 3D hand manipulation trajectories from an egocentric or first-person perspective.
Predicting 3D hand manipulation is a brutal test for a world model. I mean, it's not just about tracking a bounding box. It is a sequence of 3D coordinates over time, requiring millimeter precision to predict the approach angle, the finger placement, and the contact physics of a grass.
Oh, yeah. The trajectory metrics reflect just how difficult this is. They measure performance using average displacement error, or ADE, where obviously lower is better.
Okay.
When they tested the VGPay predictor alone, operating purely on dense frames with no global semantic guidance, it achieved an ABE of 0.071. It models the local physics reasonably well, but really struggles with the longer sequence.
And if we look at the VLM-only baseline acting as a standalone trajectory predictor, it fails spectacularly, right?
It really does. It hits an ADE of 0.142, basically doubling the error rate. It simply cannot output accurate, continuous metric space coordinates.
But ThinkJEPA, utilizing the dual-temporal perception field and the layer-wise film injection, drops the ADE down to 0.061.
Exactly. It significantly outperforms the specialized, standalone latent world model, providing the local physics engine with the VLM's global intuition, objectively improves its ability to forecast metric space.
And there is a specific ablation finding regarding the extraction module that highlights exactly why the model achieves that 0.061 error rate.
Oh, the token ablation, yeah.
Right. The performance only peaks when the pyramid extraction uses both the VLM encoder tokens and the autoregressive, or AR, tokens from the language model.
Yeah, and that finding offers a fascinating look into how information is actually distributed inside a VLM. The encoder tokens coming straight from the vision modules carry the visual content summaries. They hold the metric, what objects are in the scene and where they roughly are.
And the AR tokens.
The AR tokens reside in the language generation side. They capture the reasoning, trace the VLM actively trying to compute the why, and the semantic goal of the action.
Right, so if you drop the AR tokens and only inject the visual encoder tokens, the JEPA-predictor loses the semantic intent and the performance regresses. You need the visual summary to ground the scene and the reasoning trace to guide the trajectory.
Precisely. And we also really have to look at how this model handles recursive rollout, because forecasting the next few milliseconds is relatively straightforward, but predicting the future recursively, where you feed the predicted latents back into the model as the new past state to predict even further into the future, that is where compounding error usually destroys these models.
Oh, for sure. Drift is a massive issue.
Right. And the authors push the recursive rollout to 32 steps into the future.
Which is huge. At 32 steps, the compounding error becomes highly visible. The data shows the VLM-only baseline completely falling apart, degrading to a massive error of 1.026.
Yeah.
The standard VJPA-predictor handles the physics better, but without global context to correct its local drift, the error accumulates steadily to 0.142.
But ThinkJEPA stabilizes at 0.111 at that 32-step horizon. Yeah. The semantic guidance from the hierarchical VLM pyramid basically acts as an anchor. Even as the local dynamics model inevitably tries to drift over time, the injected global context, the persistent mathematical knowledge of what the hand is fundamentally trying to achieve, keeps the trajectory grounded.
And the qualitative heat map visualizations in the paper translate those numbers into a very clear physical reality.
Right.
They map the predicted trajectories, with blue representing early sequence steps and red representing the later steps.
Right.
When you look at the standard VJPO baseline, it suffers from what the authors term temporal collapse. The blue points simply concentrate and overlap in a small, localized region. The model knows the hand is in motion, but it loses the spatial progression over time. It basically just gets stuck.
Yeah, and the qualitative failure of the VLM baseline is even more severe. Due to the language quantization bottleneck and the lack of dense metric awareness, the VLM literally hallucinates a non-existent left hand in one of the egocentric examples.
Wait, really? A phantom hand?
Yeah. It registers the semantic concept of two-handed manipulation from the broad context of the scene and attempts to apply that text concept to a metric space where the second hand simply isn't present in the frame.
That is wild. Meanwhile, ThinkJEPA produces beautifully smooth, coherent endpoint alignment. The transition from the early blue points to the late red points tracks the ground truth almost flawlessly. The JEPA backbone provides the strict spatial temporal physics, preventing the model from hallucinating phantom hands.
Right.
And the VLM provides the logical progression and purpose, preventing a trajectory from getting stuck in a temporal collapse.
It's an exceptional demonstration of letting different neural architectures do exactly what their loss functions optimize them to do, and absolutely nothing else. You retain the strict metric space forecasting of the latent world model, and you inject the open vocabulary reasoning of a frozen VLM without ever forcing that VLM to output metric predictions.
So, synthesizing all of this for you designing these systems, ThinkJEPA proves you do not have to choose between local precision and global semantics. By utilizing a dual temporal perception field, extracting a hierarchical pyramid of intermediate VLM layers, and injecting that intelligence via a fine film modulation rather than disruptive cross-attention, you can effectively solve the temporal blindness of latent world models.
Exactly. And when we pull back and look at the broader implications of this architecture, it introduces a fascinating avenue for future engineering. I mean, think about it. If we can so effectively modulate latent world models using phrase-and intermediate layers of a VLM without ever needing to fine-tune the massive VLM itself and risk catastrophic forgetting what happens happens when we scale this guidance mechanism to highly diverse, unstructured, embodied tasks?
That's a great question.
Right. Could intermediate VLM layers serve as a universal, plug-and-play, physics-informed intuition engine for robotic foundation models across the board?
The engineering potential there is massive. You could take a frozen VLM, drop it alongside literally any specialized latent dynamics predictor, map the hierarchical layers with film, and suddenly your robotic system understands the overarching purpose of its movements, not just the microphysics of its servos.
Exactly.
You give the highly precise physics engine the ability to actually understand the intent of its actions. Thank you for joining us on this deep dive. Until next time.